And with this, we close this second session, and we move to number 3, which is planning and development. And the first speaker of this, it's Mark Kelly, that we saw him before in the questions. He has been working for 2 decades within the meteorology field, and therefore he's involved also in resource assessment and wind modeling. And as we all know, we have some standards for small wind turbines, which are defined by the IEC 600, I don't remember the number, sorry. But his question is basically, do we actually need all these standards, or are some of those too much for what we actually need? Mark, are you there?
Yeah, I'll just share my PowerPoint if that's okay.
Yes.
It's not letting me share. Let's try.
You should have all the rights. Sorry, I accidentally mute you, so you should unmute yourself. Yes, thanks. And we can see the presentation.
And yes, I'm trying to show it the whole thing. Okay, now you can see, hopefully, just
yes, yeah, perfect.
Window. Yeah. Okay. Yeah. Hi, all. Thanks. I may speak quickly. I'm not trying to sell you anything. Well, you're already sold if you're here. I apologize if I speak quickly. Yeah. So, thanks for the intro. And so this is really coming out of IEA Wind Task 41, which was about small and distributed wind, and trying to move that forward. And so, yeah, there's a bit of a background here. You can check out a report that in this IEA task that we wrote, and it really came out of a bunch of work in this task with the other authors that were part of earlier collecting and yeah, giving a lot of input, particularly Ian Baring-Gould and Trudy Forsyth. But there are some others as well, not mentioned here. So yeah, what are we talking about here? So here, this is a small wind conference, right? So there are issues still in determining, well, what is small? What are the things that the big turbine standard can cover or can't cover? Typically, due to a historical artifact, 200 meters squared rotor swept area was considered big. But nowadays, there's actually larger areas per power that are happening. So it's kind of a tricky thing. And at any rate, we're talking here, we're mostly interested here in like yet smaller stuff that's under, say, 50 kilowatts, pretty commonly. And there are various standards, like you just mentioned. Here's the number soup of, yeah, the main one, 61400-2, and then there's an update coming. Brent Somerville I saw is on, and he's involved in that, I think, in the updating. And then there's this IEC Renewable Energy Group, this stakeholder group 554, and they're making an operational document that's coming out sort of soon, 501 something about this. And on the American side, the United States, there's a new document coming out, the Small Wind Turbine 1 document, which kind of takes over for the old IEA 9.1. But anyway, the -2, this international thing, still needs to be updated. And there's also a bit on loads that we have to worry about, and that doesn't, even though it says so, it doesn't really cover small turbines very well. It still has to be adapted. That's the -13. There used to be a standard on conformity assessment, the -22, but that got scrapped, and now there's another IECRE group, SG 550, I think. There's an operational document that's coming out. Actually, I think you can get a copy nowadays for that. But again, that thing doesn't really cover small turbines totally. On the American side, they are working on that as well, I should say. Brent could say more about that. And then finally, yeah, what about testing these things? Power performance testing has been a problem in turbines, for small turbines for a while. There is an annex of the -12, but I won't even go into that because, yeah, the -12 is getting split into, it's in 2 right now, but it's getting split into like 9 parts or something. Also, I should apologize. I'm sick. I don't have COVID, but I might sound a little odd. So hopefully you can understand me okay. Because I'm in presenter view, I can't see the screen at all. So just interrupt me if there's something, if there's an issue. Okay, so yeah, some context, right? So I come mostly from wind resource assessment. I'm a turbulence and fluids and meteorology guy. And so like if we look physically, like flows and stuff, yeah, what small turbines have been around for a long time, right? What was around 40 years ago versus now? Well, in the first generation, just as now, small turbines are often located in the atmospheric surface layer, which is pretty well known. They're not all that commonly necessarily pitch regulated. That is, they're regulated in different ways, like stall regulated. And observations for these things, local observations where a turbine might be sited, tend to be limited. Yeah, they're easier to get because you don't need a really tall mast, a little cheaper, but they tend to not be like very long time measurements, and they often, because the environment, aren't necessarily very representative of what a turbine will experience. What will a turbine experience? Well, quite variable wind conditions with huge perturbations of velocity, a lot of turbulence stuff, nonlinear stuff, and so strange statistics compared to what large wind, multi-megawatt wind turbines see. That is, you don't have Weibull distributions all the time. It's hard to actually get distributions of wind speed in some places. And the directional dependencies can be really wacky too, because maybe there's a tree on one side and a house on the other side, affecting a turbine. And also, this is basically, in terms of simulation, if you're a CFD wonk, this is like a bottom-up flow problem. So it's very, very much what the environment of the flow environment of small wind turbines is really dominated by the surfaces, by the ground, by obstacles. And so there's all sorts of different flow phenomena that just look like turbulence. And yeah, so there's not a lot of top-down stuff. And then again, with measurements, it's tricky because often the sample lengths aren't, they're not a year long. They're not very representative in the long term. And then there's all sorts of flow distortion, both by, say, the instrument, but it can also be due to the instrument. You might have a little anemometer that's too close to a house or a tree or whatever. And so you have external flow distortion that can influence the anemometer. And yeah, the measurements might not be taken exactly where the turbine would be. All right, so that's sort of the physical context, right? But what do users want? So in the IEA task, we've had like 3, over the last few years, we've had 3 end user stakeholder workshops. And through those, there was a like research priority survey that we ended up making, and then people responded about that. So industry people and such, for small wind. And yeah, a number of points kept coming up. We had like one workshop was in the US and in Washington, I believe it was 2019 or 20, and then another one in Ireland on the European side. There was supposed to be yet another in the University of Inner Mongolia, but the pandemic kind of scrapped that, so we didn't have that yet. So anyhow, so a number of things come up, like first, so here I have these things listed with priorities, that H for high and M for medium. So the highest priority things, as denoted by like the survey. So first is trying to open markets for so-called medium wind turbines. We won't deal with that here. Another thing is, yeah, getting better aeroelastic models, and actually a path to validating models. Yet another was trying to get more accessible loads testing and characterizing loads. That is, this -13 isn't really adapted for distributed wind or small wind. Other things, especially in the US, came up were like duration testing instead of loads testing. It's too expensive, too long, too hard. And then also turbulence. How do we deal with turbulence and characterize it? Next, power curves. How do turbines really perform? Because the power curves don't actually often look the way that the manufacturer tells you. because of how one might mount the turbine and where it is. And then also tower dynamics interaction was a thing listed, and then also micro turbines, so like turbines below say 2 or 3 kilometers where things change, needs to be addressed. So all of these things were put into, like in the report that I showed at the beginning, the first slide I showed a little opening page from the report that includes this table summarizing these key challenges and with their priorities, as well as the different standards. Because there's numbers are so long, you know, IEC 61400, I've just dropped that IEC 61400, so -2. So you see at the different forums on the European and American sides, these workshops that we've had show where these different issues that I just listed were identified. And then also in this table, there's a few lower priority things as well. Simplified loads models, blade testing, noise testing, and safety and function testing as well. So these have been identified, and okay, so what do we do about it? Well, there's a few things. So in general, as elucidated in this report, we have to deal with, for example, reclassifying turbines into, say, more classes, or ones which are appropriate for, say, micro turbines versus small turbines. You know, where there's, for small turbines, as you all probably know very well, you know, different RPMs, the control systems are different. The output range is different. They deal with different markets and lifetimes, expected lifetimes. And then again, as I mentioned, you know, between 2 and 3 kilowatts, there's kind of a sort of a transition from operating regimes for most topologies, for most kind of design types of turbines. And then, okay, certification and testing requirements, basically for small turbines, they have tended to be prohibitive, like too expensive, too hard. In particular, the duration of loads tests are pretty, cumbersome and long, and difficult, maybe hard to even understand. I mentioned here the China example. So what does that mean? You can look in the report, but basically in China, especially towards micro turbines, there are a set of voluntary standards which have helped push things along in that area. So it's giving options to small turbine manufacturers, for better or worse. So another issue was that, the conformity assessment is inadequate. Well, the -22 went away. It was never really great for small turbines. And so at the end of the day, a clear method to determine and show and report whether or not a turbine, it conforms to standards, it needs to be made. So we're just missing that common approach that small turbine manufacturers can understand and like document their stuff with. And then back to, an issue that it's a tricky one, and it depends on what market you look at, maybe. But for small turbines below tens of kilowatt, especially, like validated aeroelastic modeling, the most aeroelastic models were, they're best for the big turbines, megawatt or bigger. And they need to be adapted for smaller ones, different design types as well. And then loads testing itself, so not just the aeroelastic modeling, but the loads, it tends to be expensive prohibitively. What about turbulence? Well, like I mentioned earlier, we have different turbulence regimes depending on where you place a turbine and how the turbulence will affect a turbine. It depends on the size and the type of design you have for a turbine, right? So that needs to be addressed. As I mentioned also previously, the power curves in crazy non-uniform flow situations, complicated flow situations, these need to be better documented and tested as well. And another thing that happens, as you all probably know, is small turbines can have resonances that are at frequencies that show up in the tower dynamics, like they overlap with important tower dynamics, same scales. So that needs to be treated. Okay, what about like some of the ways that small turbines are given allegedly a shorter path, the simplified loads model, SLM? Well, those are simplified models with like kind of conservative safety factors instead of being, complex models. They end up with pretty big conservative safety factors, which can also be like a little too conservative and not helpful. And a lot of folks are going over to aeroelastic models. So this needs to be tested and sorted out. And then blade testing itself for small turbines, some failures happen that should have been caught. That's been documented anecdotally a bunch of times, especially in the US. Higher rotation rate, that can lead to various things. And then last, acoustic testing, it seems a bit too demanding for small turbines. Yes, there can be tonal issues, but the test needs to be simplified or translated. And then lastly, safety and function testing. How do we do that? And that's been identified as a low priority, but still it needs to be determined, like, hey, are just power and simple RPM, is that enough to determine the function testing, for example? Okay. So part of this work in the IEA Wind Task Group is like about what research is needed. I see something in the chat here. Okay. So what research is needed? So there's a few things. Let's see. Yeah, there's a few things. Following along that table I showed earlier in the report, we have like research needed for each thing. So I'll go through like the main points here. We want to just try to support scientifically the adjustment of standards, right? Improving them. So really it depends on data. A lot is on data and validation. But first things first, trying to get new classifications. So like size, types, and classes. And following from that, of course, comes conformity assessment. But really, we need more measurements like speed, power, rotation rate, turbulence intensity. We need to aggregate those. And we need to do it for different turbine topologies and also for smaller turbines. So if we can look at study power output and behavior of different turbines by aggregating all these data, then we can do parametric studies across these different sizes and types, and then see, okay, what kind of power limits are reasonable, like to separate the turbines into new classes. And then also, it would be nice to put together, okay, what lifetimes and failure rates are actually found in various small turbine topologies, and also sort them like according to different conditions as best we can, to better inform about, say, turbulence, for example. And then the requirements for certification and testing, that's been a real hindrance for a lot of manufacturers getting to market. It's been identified over and over. And so like there's these issues like how much duration testing is actually relevant for small turbines, particularly the really small ones below a few kilowatts. And also like less complex aeroelastic models, which SWT1, I believe, is starting to cover. They need to be validated better in different conditions across many different sites, and for different turbines. Further research is to actually, along those lines, further in aeroelastic models, we got to find what are actually the model inputs that are like most needed, and this may change for different turbine sizes and configurations, and then we need to actually have a validation methodology. So that's kind of an iterative research process, still needs to be done. And the loads testing as well. First, we got to find out, okay, how bad is the -13, and how bad is it as a function of size and type of control, regulation, as well as like design, vertical axis wind turbine versus HOTS versus some shrouded stuff, just to name a few. And can we reduce the requirements for yaw pitch controls? That needs to be studied as well. And then turbulence. This is something that there's a bunch of different aspects, but kind of the main ones are looking at the normal turbulence model to re-examine it. We just need more 3D velocity measurements at various sites, and the representative sites, the kind of sites where turbines tend to be, preferably moving these measurements around. and determining what is representative. That's not even necessarily known. Where are small turbines of different sizes? What kind of environments are they really put in? So, or shall we recommend they be put in? So basically some connecting things, things need to be connected together. So like results that are already existing, as well as research, and plus the theory, like the stuff I work with, atmospheric turbulence theory and obstacles. So this stuff kind of has to be amalgamated to get sort of to the next generation of like easy enough turbulence modeling that's appropriate. And then of course, then there's the turbines themselves, what they can withstand. So different turbines, different sizes. Yeah, with the aeroelastic codes that are available, okay, got to see how much loads end up coming out for various input. And so we, with different turbulence model input. And so the loads end up needing to be compared. Another thing that needs to be treated is different peak length scales in different places. The measurements, more sonic anemometer measurements can drive this. This is research stuff. And then in the end, we get different metrics for both aeroelastic simulations and simplified load models. That's what we want to find. All this stuff, of course, has to be documented and then redone, iterated with more and more data sets. All right, I feel like I'm taking too much time here. Performance and conditions, we got to get into obstacle models to get better, basically, predictions of like what's the wind speed going to do in a given place, just for citing these things. And then also for turbulence, that's really hard and still lagging. So RANs, that is CFD, that research on that can help improve some of the simplified models that we do have. And again, we need like 3D sonic anemometer type observations more. Further, kind of putting this together with power curves from turbines that have been observed in different operating regimes. Yeah, the aero modeling comes after that as well. And then modal tests, that's also underway. Like, for example, University of Vienna, I believe, and others are doing that. So like getting better handle on damping factors with modal tests, using different weights, turbines on top of different towers, different sizes. And so, yeah, that can be translated hopefully into like a simplified method for example, free yaw turbines to deal with tower resonance. Lastly, the simplified loads model to make it easier towards certification. Got to find out where is it applicable and how bad, how limited is it? So what size limit, does the current SLM really apply to? And then further things like fast spinning small turbines, got to deal with gyroscopic loads, and as well as passive yaw or active yaw. What are the load cases that really should apply to those, and reducing safety factors through that kind of research. Power production faults, different, shutdown and startup regimes, load cases. That it's kind of like the -1 needs to be better developed. On and off grid turbines, what are the fatigue thresholds? And then back to SLM, downwind turbines, maybe they have a different set of SLM parameters. And also, if they're not design driving, the SLM load cases that we have, maybe we just get rid of some of them. And then, of course, yawing, there's still a problem with. Yeah, we need to match what's going on with yaw rate stuff and as observed versus what's assumed in the SLMs. And then lastly, there's this Danish way of this 300 Newton meter method for quick and dirty, maybe not dirty, quick way of determining like expected loads. Parametric study on that could be done. Okay, so blade testing, high RPM stuff. And we need actual strategy to reduce safety factors. That's just through fatigue testing. And then, of course, for the really small ones, the few kilowatts and smaller, we need full rotor testing. In the end, like, why do some blades actually fail, but not during tests? Looking out over lots of test results, which now exist in the last almost 20 years since the -2 came out, the last edition of the -2, we can do this. And then lastly, like noise testing, just got to simplify. And is it even worth having this tonal audibility thing? So the new, I should say the new -11-2 standard, which is coming out, I was sitting in that for a while. I was an acoustics guy 25 years ago. That needs to be harmonized as well. But this stuff still needs to be translated for small turbine manufacturers. And then also the noise stuff, okay, it needs to be tested like, hey, does this even work for other topologies like vertical axis wind turbines? And then safety function testing, a lot of this is kind of like the aeroelastic validation and testing. But here now we're talking about duration tests. We just got to aggregate data, like all the existing test sets, and find patterns and trends to see if we can make the safety and function test easier. And one of the bits is like, we need to find out, hey, is it only RPM and power that are needed for this function testing for microturbines or not? So a bunch of recommendations came out of this. And the clock here, basically updating the turbine classifications, as I mentioned. Certification and testing requirements need to be made sort of easier, but per updated classes and types. Conformity assessment is so vague, we just need to clearly document that, but there is an operational document coming on that along those lines. Aeroelastic models, we need better adapted to small, and yeah, and there's more research there, but a clear validation path is needed. That's something for the standard. The -13 can be maybe have an annex added for loads testing for small turbines, at least the horizontal axis ones. New class has been recommended going back to IEA Wind Task 27, but then there's still some debate around that as well. It depends if you talk to Japanese community versus American community versus European. It's hard to see if there really still is a consensus, but at any rate, some new class is likely to be recommended. The performance, yeah, basically updating the -2 to accommodate like having more than one power curve for different conditions, different range, turbulence intensity ranges, for example, because different power curves are coming out, and it's better for the manufacturers to have trustable curves, for the consumers. So the reporting requirements also, there's all this bureaucratic sort of work. Like the reporting requirements need to be like made consistent with these other standards. And yeah, a lot more research needed with tower dynamics and SLM. And yeah, the noise testing, basically just some simplification and translation needed in the current noise, in the current turbine noise thing that exists. Along the lines of recommendations and results, as it can be seen in the report, because I think I'm going over time, we've divided up into like tentatively different categories. So like the two on the left, we're especially interested in here, micro and small, with vague borders on rotor swept area and nominal power, and people can of course debate these. And so yeah, what I've just mentioned above is basically listed here. Some of the things that we recommend are more towards micro turbines, and some are more towards small turbines. For example, like the requirements for micro wind. Aeroelastic modeling is more for small turbines than micro turbines. Anyway, I'll point at this chart instead of talking all the way through it. I'll say, well, the X's means that, yeah, this corresponds to that size. So we need normal turbulence model to be updated as well as tested for all three sizes here. But I'll just guide you to the report instead of just reading what's on the page. So all the things I've mentioned, these like basically 12 categories or 12 points, they all have recommendations that come for them. So yeah, so at that, I'll stop talking, and I don't have a link, but I can send one out to the reports so that you can more easily read it. Hopefully there's time for questions.
Yeah, thanks a lot. I mean, we are a little in the lunch break, but of course I can see already that there is a question from or a comment from Fritz. Let me see. I don't know if you want to.
Yeah. So Fritz asked, what about the medium? Yeah. So just high. He asked about like, what is high priority? it was identified in the survey of the stakeholder groups and researchers and stuff in these workshops, high, medium, or low priority. They were just asked to say, hey, these different issues that you've come up with, what is a priority? And they just said high priority for that. So that is dealing with what is large and not large, what is large and what is medium. Yeah, and to what extent, in which areas should turbines from say 50 to 500 kilowatts have to follow the -1. So for example, with some loads testing stuff, maybe they shouldn't. Yeah. Estimate of time. You said, can you give, so Fritz asked if I could give an educated guess estimate of time. No, an educated guess, I could give lots of guesses. The -2 is being updated starting, I think, next year. There are some stuff coming already out of SWT1 that's useful for some of their elastic stuff. There's a workshop next month about that. So this SG 554 group, that operational document's coming out this year, I think. A similar group for the conformity assessment has something coming out as well within the year. However, as I pointed out, some of the things involve research, so it's going to be multiple years before we can get anything. There's also the standards update cycle. So yeah, it takes time. It takes a few years to update, but the -2 probably is going to be updated within a couple of years. The -13 might be a little harder, and the -12 even harder. And then, yeah, Brent just wrote, very nice. Yeah, so the ACP small wind turbine standard, SWT1, this gives a limit already at 150 kilowatts, as opposed to something that would be more like, 50 kilowatts between small and medium, as suggested in the document that I pointed at. Hopefully that helps.
Any more questions? Doesn't look like. But yeah, thanks a lot for the presentation, and hope you stay on board, because I can see that there are some discussions going on. So of course, then yeah, you're welcome to further discuss the topic. So we'll have the lunch break in our case, a longer break if you are somewhere else in the world. And we will meet in at 2 CEST time, which is in 45 minutes roughly. Have a good break.